Hello, my name is Michael Ramage, and I'm President and CEO of Asemblon Incorporated in Seattle, Washington. Thank you for this opportunity to speak with you today. We believe our technology is the future of hydrogen and can have an important role to play in addressing climate change. We all know that hydrogen is an abundant potential energy source and that there are numerous ways to make it. The problem has been, historically, that once you compress it, it makes it not cost competitive with hydrocarbon fuels. Today, most hydrogen is stored and transported all over the world under compression. However, it is well known that the cost to compress gaseous hydrogen is what makes its price too high for widespread commercial use compared to gasoline or diesel fuels, that the volume of hydrogen one can deliver under compression is limited, and that the bleed off of hydrogen from a pressurized vessel quickly reduces the amount of available hydrogen. By eliminating this equipment expense and process, we can make hydrogen costs competitive with hydrocarbon fuels. Our company is developing a family of liquid organic hydrogen carriers that we call Hydroline that store, transport, and dispense hydrogen at room temperature and without the need to pressurize it. This process involves chemically binding the hydrogen to the carrier molecule, a commonly performed process called hydrogenation, and then selectively removing the hydrogen for energy use on demand. Our technology works with hydrogen regardless of how it is produced: steam methane reforming, electrolysis, etc. Since we will store and transport hydrogen in a liquid form at ambient temperature and pressure, much of the existing tanks and piping currently used in the storage and distribution of hydrocarbon fuels can be utilized with our carriers. This will greatly reduce capital expenses for deployment and encourage adoption of our technology. The material safety data for our carriers is very similar to that of gasoline, and ultimately, we'll be able to produce our carriers from biomass. Hydrogen will not release from our carriers unless in the presence of our proprietary catalyst and at a temperature of 200 to 230 degrees centigrade. You could spill the liquid on the ground and the hydrogen will not release. Our carrier liquids have hydrogen storage capacities ranging from 6.7% hydrogen to 13.6% weight by weight. These are called gravimetric capacities. Our tests have demonstrated that we produce 99.99% pure hydrogen from our reactor without catalytic coating, and that we can remove hydrogen from our carrier molecules, capture the spent carrier by condensation, and then attach new hydrogen to the original carrier many times over without significant degradation of the liquid. The carrier then functions like a regenerable battery. Unlike other carrier technologies, we can store hydrogen on board a vehicle and release it from the carrier using our reactor system. And for stationary hydrogen storage, our calculations and those of others show that we can store approximately 3.2 gigawatt hours of energy as hydrogen in a 30-foot by 60-foot non-pressurized tank using our carriers. There are two other types of liquid organic hydrogen carriers currently being commercialized. They are toluene, or methylcyclohexane, MCH, and ammonia. Toluene has a gravimetric capacity of approximately 6%. This volume is not suitable for storage and dehydrogenation on board most moving platforms, cars, trucks, etc., because the volume of liquid needed to provide sufficient range requires too much storage area on the vehicle. Further, MCH requires a temperature of approximately 400 degrees centigrade in order to remove the hydrogen in a reactor unit that measures, from what we estimate, at about 20 feet long, clearly not suitable for mobile uses. We are aware that Chiyoda International is transporting hydrogen from the Middle East using this carrier. An independent assessment has determined that only our second highest capacity carrier, which is 10.8%, will transport 74.5% more hydrogen on the same volume that MCH does. And we have even higher capacity carriers and maybe even more attractive. With other LOHC carriers, the hydrogen must be compressed once delivered in order to accommodate most current uses. This would not be the case for Asemblon's technology, as the hydrogen is extracted from the reactor in an uncompressed condition, and hydrogen production can occur at a stationary use site or on board a vehicle. Further, since the dehydrogenation temperature for toluene is approximately 400 degrees centigrade, one can expect greater molecular degradation of the carrier over time with related carrier replacement costs. Please note that both toluene and ammonia require noble metals in their catalysts, whereas Asemblon's Hydroline carriers will not. Ammonia has a gravimetric capacity of approximately 17%, but ammonia simply delivers hydrogen one time, and the nitrogen resulting from the dehydrogenation of the carrier is off-gas to the atmosphere. Like toluene, the dehydrogenation reactor is very large, so ammonia is only suitable for stationary hydrogen uses unless you were to recompress the hydrogen, which again causes the hydrogen to be too expensive for wide adoption. The temperature required to remove hydrogen from ammonia is approximately 600 degrees centigrade. This energy requirement needs to be factored into the process to determine the amount of net energy that is provided. Clearly, the 17% capacity is offset to some degree by the energy cost to dehydrogenate at so high a temperature and the capital expense of large dehydrogenation reactor systems. Ammonia also has safety concerns that can be life-threatening. These are dehydrogenation reactors for MCH and ammonia. As you can see, these reactors cannot be deployed on most mobile platforms. Asemblon's Hydroline reactor system is being designed to measure approximately 1 cubic foot and will, in its first configuration, have hydrogen production of approximately 2,200 gaseous liters per minute. Our technology can be deployed in almost all platforms currently using hydrocarbon fuels: buses, locomotives, fleet vehicles, ships, industrial equipment, military applications, and large-scale municipal storage. Looking forward, it is our expectation that once commercially demonstrated in several use cases, there will be high demand for our technology. We believe that EVs are only part of the environmental solution and that they come with challenges, including upgrading of the transformer networks and the fact that much of the lithium and other rare earth metals used in EV manufacturing are under the control of governments that are not necessarily aligned with our best interest. Even with just a few static storage only requirements that we've already identified, our expectation is that we will generate sufficient revenues early on to reduce the likelihood of further equity dilution after the current round. Thank you very much for your kind attention today. I welcome your inquiries should you have any questions regarding this important technology. My numbers are on this screen.